Welcome to the first lesson of our Java course on modern practices. Today we're diving into modern object creation in Java. Not just how to create objects, but how to design them so they scale well, remain correct over time, and take full advantage of modern Java features and frameworks. This is not a beginner's tutorial. I'm assuming you already understand programming and object-oriented concepts, whether from Java or another language, but you might not be familiar with the latest Java capabilities and best practices. Here's what we'll cover: fundamentals, constructors, fields, methods, visibility, encapsulation, and validation, the building blocks of safe object design. Static members, when and why to use static fields and methods, and how to create utility classes correctly. Immutability, why immutable objects matter, how to implement them, and how modern Java features like records make this easier. Validation, ensuring objects are always in a valid state, using defensive programming and helpers like objects.require non-null. Inheritance and alternatives, when inheritance makes sense, and why interfaces and composition often lead to cleaner, more flexible designs. Modern features, using records, enums, and sealed classes to model data and constraints effectively. Object creation patterns, static factory methods and the builder pattern, solving problems like telescoping constructors and invalid states. Dependency injection, the concept, why it matters, and a quick look at how frameworks like Spring automate it. Object reuse and lifecycle, when to create new objects, when to reuse, and how to manage expensive resources safely. Primitives versus wrappers, performance considerations, nullability, autoboxing, and avoiding hidden costs. By the end of this lesson, you'll have a mental model for object creation in modern Java. So every time you design a class, you make intentional, informed choices rather than just adding another constructor. If that sounds useful, let's get started. Before we jump into advanced patterns and modern features, let's ground ourselves in the basics, because even in 2026, the fundamentals still matter. Let's start with the absolute basics of creating objects in Java. In Java, every class can define a constructor, which is a special method that initializes the object. Here's a simple class, person. It has two pieces of state, a name and an age, and a constructor that sets them. To create an object, we call the constructor with the required arguments. The constructor's job is to make sure the object starts life in a valid state. If a field is required, make it a constructor parameter and validate it there. Next, fields and methods. Fields represent the state, what the object knows. Methods represent behavior, what the object can do. In Java, we almost always make fields private. That's the first step towards safe design. Notice what we're doing. We're exposing behavior, celebrate birthday, instead of exposing the age field directly. That keeps the class in control of its own invariants. Now, let's talk about visibility and encapsulation, two ideas that protect your design. Visibility controls who can see what. Encapsulation means hiding internal details and exposing only what's necessary. Here's a bad example in which name is a public field. Anyone can change it, and you lose control. In the second version, the field is private, and we offer a controlled way to read it. Setters are optional. Only add them if external code should be allowed to change the state. When you do expose mutation, do it through meaningful methods that enforce your rules. The guiding principle is simple. Keep internals private, expose clear behavior, and make sure objects are valid from the moment they're constructed. That's the foundation: constructors for initialization, fields and methods for state and behavior, and encapsulation for safety and flexibility. With this in place, modern features like immutability, records, enums, and sealed classes become much easier to use correctly. Now let's talk about static fields and methods. These belong to the class itself, not to any individual object. Think of a static field as shared data. Every instance of the class sees the same value. Here's an example, a counter that tracks how many person objects have been created. Notice two things. The count field is static, so it's shared by all person objects. And the getCount method is also static, so you call it on the class, not on an instance. Static members are great for constants, utility methods, or shared state, but use them carefully. Too much shared state can make your code harder to test and maintain. Now, let's talk about immutability, one of the most important principles in modern Java design. An immutable object is one whose state cannot change after it's created. Once you set its fields in the constructor, that's it. No setters, no mutation. Why is this so powerful? Because immutable objects are inherently thread-safe, easier to reason about, and less prone to bugs caused by unexpected changes. Notice the key points. The class is final, the fields are private and final, and there are no setters. Once a person is created, its state never changes. If you need a different value, you create a new object instead of modifying the old one. This approach makes your code safer and more predictable. Modern Java makes immutability even easier with features like records, which we'll explore next. Now, let's talk about something critical: making sure your objects are always valid. A well-designed class should never allow an invalid state, not when it's created and not when it changes. The first line of defense is the constructor. Validate all required parameters before assigning them. Here's an example. A person must have a non-empty name and an age greater than 0. This guarantees that once the object exists, it starts in a valid state. But what if your class allows changes later? Every method that modifies state must enforce the same rules. Never assume the caller will pass valid data. Always check. This is called defensive programming, and it prevents bugs from creeping in. The principle is simple. Validate early, fail fast. If something is wrong, throw an exception immediately rather than letting the object live in an invalid state. This approach makes your classes robust and predictable, and it's the foundation for building reliable APIs. Now, let's look at a quick way to enforce non-null values in your constructors. Java provides a utility method called objects.requireNonNull. Here's how you can use it. Objects.requireNonNull checks the value and throws a null pointer exception with your custom message if the argument is null. This makes your constructor cleaner and avoids manual if checks. You can also use it in setters or any method where you need to guarantee a non-null argument. The key takeaway: validate early, fail fast, and keep your code readable. Now let's move on to another core concept in object-oriented programming: inheritance. Inheritance allows you to create a new class that reuses, extends, or modifies the behavior of an existing class. It's a way to model is-a relationships. For example, a student is a person. Notice a few key points. We use the extends keyword to declare that student inherits from person. The student constructor calls supername to initialize the parent part of the object. Student automatically gets all the methods from person, like getName. Inheritance is powerful, but it comes with responsibilities. 1. Use it for true is-a relationships. If student is a kind of person, inheritance makes sense. But don't use inheritance just to reuse code. That's a common mistake. 2. Avoid deep inheritance chains. Long hierarchies are hard to maintain and understand. Prefer composition over inheritance when possible. 3. Understand method overriding. A subclass can override a method from its parent to provide specialized behavior. 4. Visibility matters. Protected members are visible to subclasses, but private members are not. Use getters or constructors to pass data down safely. Inheritance is useful, but it's not always the best solution. In fact, modern Java encourages using interfaces and composition for flexibility and cleaner design. Why look for alternatives? Deep inheritance chains can make code rigid and hard to maintain. If you need to share behavior without forcing an is-a relationship, Interfaces and composition are better choices. An interface defines a contract, what a class can do, without dictating how it does it. Here, report promises to implement print. Interfaces let you add capabilities without locking into a class hierarchy. A class can implement multiple interfaces, which is something inheritance cannot do. Composition means building a class by combining other objects instead of inheriting from them. Here, report uses a printer internally. This is more flexible than inheritance because you can swap out the printer implementation without changing the report class. Why prefer composition? It avoids tight coupling. It's easier to change behavior at runtime. It keeps your design modular and testable. Modern Java gives us powerful tools to make object modeling simpler, safer, and more expressive. Let's look at 3 key features: records, enums, and sealed classes. Records are a concise way to create immutable data classes without boilerplate. That's it. This single line gives you a class with private final fields, a constructor, getters, equals, hashcode, and toString. Records are perfect for modeling simple data carriers. They're always immutable, so you don't need to write setters or worry about state changes. Enums let you define a fixed set of constants with type safety. Instead of using strings or integers for states, you create a dedicated type. In the example, we define an enum called day with 7 constants, Monday through Sunday. Each constant represents a day of the week. This is much safer than using raw strings because the compiler enforces valid values. We also make the enum more powerful by adding fields and methods. Each day has an associated type, either workday or weekend. We declare a private field called type inside the enum. Each constant calls a constructor with its type. For example, Monday passes workday, while Saturday and Sunday pass weekend. Finally, we add a getType method so you can retrieve the type of any day. This shows that enums aren't just constants. They can hold data and behavior, making them perfect for modeling categories or states in a clean, type-safe way. Sealed classes allow you to restrict which classes can extend or implement a base class. This is useful when you want a closed hierarchy, meaning only specific subclasses are allowed. In the example, we define a sealed class called shape. Right after the class name, we use the permits keyword to list the allowed subclasses, circle and rectangle. This means no other class can extend shape. Next, we define circle and rectangle as final classes. Making them final ensures they cannot be extended further, which keeps the hierarchy simple and predictable. The benefit of sealed classes is that the compiler knows all possible subclasses. This makes pattern matching and switch expressions safer. For example, if you write a switch on shape, the compiler can check that you handle every possible case, circle and rectangle, and warn you if you miss one. This feature is great for modeling domains where the set of types is fixed, like shapes, states, or commands. It gives you control and clarity without sacrificing flexibility. Now that we've covered the fundamentals and modern Java features, let's look at object creation patterns. These patterns give you more control and flexibility than plain constructors. A static factory method is a method that returns an instance of a class. Instead of calling new directly, you call a named method. This improves readability and allows you to manage object creation internally. Here, the constructor is private, and we expose a static method called of. This makes the creation more expressive and allows us to add logic later, like caching or validation, without changing the API. Static factories can also return subtypes or pre-built instances, which constructors cannot. When a class has many parameters, using constructors or setters can lead to serious design issues. First, if you add multiple setters, the object cannot be immutable. It also means the object can exist in an invalid state between setter calls. For example, you might create a person and forget to set the age. Now you have a partially initialized object, which is dangerous. Second, if you try to solve this by writing many constructors for different parameter combinations, you end up with what's called a telescoping constructor problem. Imagine a class with 5 or 6 parameters, some optional. It quickly becomes unreadable, especially when several parameters share the same type, like multiple string arguments. It's easy to mix them up. The builder pattern solves both problems. It lets you set properties step by step in a controlled way, and then create the object in one go, ensuring it's valid and immutable. Here you create a builder, set the fields you need, and then call build to get the final object. This approach is readable, avoids invalid states, and keeps the final object immutable. It's especially useful for classes with many optional parameters. Now let's talk about dependency injection. This is a design principle that makes your code more flexible and easier to test. The idea is simple. Instead of a class creating its own dependencies, you give them to the class from the outside. This means the class doesn't need to know how to build its collaborators. It just uses them. Why is this important? Because it removes hard-coded dependencies, makes your code more modular, and allows you to swap implementations easily, for example, in tests. Imagine we have a report service that needs a printer to print reports. Without DI, the service might create the printer itself. This is rigid. If you want a different printer implementation, you have to change the class. With dependency injection, we pass the printer in through the constructor. Now report service doesn't care which printer it gets. It just uses it. You can inject a real printer in production and a mock printer in tests. This makes your code flexible and testable. Frameworks like Spring take this concept further by automating the wiring of dependencies. Instead of manually creating objects and passing them around, Spring uses configuration and annotations to inject the right dependencies at runtime. But the principle is the same. Classes don't create their own dependencies, they receive them. Finally, let's talk about object reuse. When should you create new objects, and when should you reuse existing ones? Sometimes creating new objects is fine, especially if they're lightweight and immutable. But for expensive resources like database connections, file handles, or large caches, creating them repeatedly can hurt performance and waste memory. The solution is to reuse these objects when possible, either by keeping a shared instance or using an object pool. Frameworks like Spring also help manage lifecycles automatically. Here, instead of creating a new printer every time, we reuse a single static instance. This works well if the object is stateless and thread-safe. If it holds mutable state, reuse can cause bugs, so always check before sharing. Occasionally, you'll want a class that exists only as a grouping of static methods and static fields. For example, a utility class like math or collections. In these cases, you don't want anyone to create an instance of the class. The best way to enforce this is to make the constructor private and throw an exception if it's ever called. Adding a clear comment helps future developers understand why. Here's what's happening. The constructor is private, so no one outside the class can call it. Inside the constructor, we throw an assertion error to prevent accidental calls from within the class. The comment explains the intent. This class is a utility holder, not meant to be instantiated. This pattern makes your intent clear and prevents misuse. Another important topic are primitive versus wrapper types. In Java, primitives are built-in value types like int, boolean, and long. They store raw data and are extremely fast and memory efficient. On the other hand, wrapper types like integer and boolean are immutable objects that encapsulate primitives, enabling object-oriented features such as generics and collections. Use primitives for computation-heavy, non-nullable, performance-critical code, for example loops, math operations, or counters. When to use wrappers? Use wrapper types when object semantics are required, for example, working with generics or collections like list of integers, allowing null values, using frameworks, reflection, or APIs that expect object. Wrappers make primitives compatible with Java's object-oriented features. autoboxing and unboxing. Java automatically converts between primitives and wrappers. Autoboxing, converting a primitive to its wrapper. The compiler inserts calls like integer.valueOfInt. Unboxing, converting a wrapper back to its primitive. The compiler inserts calls like int value. This is convenient, but be careful. Excessive boxing and unboxing can hurt performance in tight loops. Let's wrap up what we've covered in this lesson on modern object creation in Java. Fundamentals. Start with solid basics: constructors for initialization, private fields for encapsulation, and methods for behavior. Validate inputs early to keep objects in a valid state. Static members. Use static fields and methods for shared data or utility functions. For utility classes, make the constructor private and throw an exception to prevent instantiation. Immutability. Immutable objects are safer and easier to reason about. Use final fields, no setters, and consider modern features like records for concise immutable data classes. Validation. Always check object validity in constructors and any mutating methods. Use helpers like objects.require non-null for cleaner code. Inheritance versus alternatives. Use inheritance only for true ISA relationships. Prefer interfaces and composition for flexibility and cleaner design. Modern features. Records simplify immutable data classes. Enums model fixed sets of values with type safety. Sealed classes restrict inheritance for controlled hierarchies. Object creation patterns. Static factory methods improve readability and flexibility. Builder pattern solves problems with telescoping constructors and multiple setters, ensuring immutability and readability. Dependency injection. Pass dependencies from the outside instead of hard coding them. This decouples your code and makes it easier to test. Frameworks like Spring automate this. Object reuse. Create new objects freely when they're lightweight and immutable. Reuse heavy resources carefully, and rely on frameworks or pools for complex life cycles. Primitives versus wrappers. Use primitives for performance-critical code. Use wrappers for generics, nullability, and APIs that expect objects. Understand autoboxing and unboxing to avoid hidden costs.